I didn't see you there. Lovely day, isn't it? Too bad I forgot to bring my sunscreen. Anyway, welcome to the first edition of Seaside Science, where we discuss evolutionary science at the beach. Today, for my first video, I thought I'd talk about one of my favorite undersea tricksters, the mimic octopus, a video of which you can see by clicking on the link below. Before we get into the specifics of this chameleon of the sea, I'd like to take a moment to discuss the camouflaging abilities of cephalopods as a whole. Cephalopods, members of the molluscan class Cephalopoda, are characterized by bilateral body symmetry, a prominent head, and a set of arms or tentacles. They're found all over the world in varying water temperatures. A very ancient group, cephalopods first appeared in the late Cambrian period. The cephalopods we see today, octopi, squid, and cuttlefish, most likely came into being after diverging from their primitive ancestors about 438 million years ago. This was during the Ordovician period, when cephalopods were a big deal in the ocean. Today, fish are the kings, but I think cephalopods will make a comeback. The majority of cephalopods are skilled shapeshifters, so much so that they put the famed chameleon to shame. What's so special about them is how rapidly they can change color, as well as the complexity of color patterns they are able to produce. This ability comes from 3 layers of cells stacked one on top of the other, all working together. First, there are the chromatophores, which make black, brown, red, orange, and yellow. These cells include elastic saccules that hold pigments attached to 15 to 25 different muscles. When a cephalopod contracts or relaxes these muscles, the saccule widens or shrinks, allowing the pigments inside to show or disappear. From this process, cephalopods can produce a variety of patterns, even moving ones, as they have the ability to contract one saccule while relaxing the other. Second, there are the iridophores, below the chromatophores. These produce metallic greens, blues, and golds in some species, and also a silver color around the eye or the ink sac of others. Cephalopods use these to reflect light and to conceal their organs. The colors can change, but not via muscles or neuromeans. Rather, they change in response to fluctuating hormone levels, making the changing process slower. The last layer is made up of lucifores, flattened, branched cells which manipulate incoming light and reflect the predominant light wavelength in any given environment. This allows cephalopods to blend in with their surroundings. Some deep-sea cephalopods also come equipped with photophores, which produce light via bioluminescence, kind of like a glow stick, making the cephalopods glow either constantly or intermittently flashing. It is important to note that some deep-sea cephalopods have few to no chromatophores. Because they live in the deep ocean, there's very little light, rendering camouflage redundant. The deep sea octopus is a very good example of this. Why, you ask, did cephalopods evolve this bizarre and fascinating cell network? The answer is, we don't really know. The fossil record at the moment does not provide scientists with enough conclusive information. However, they can make several educated guesses. Their first guess is that it was probably a camouflage thing, or rather, in more scientific terms, crypsis, which means the ability to blend in with the environment. For soft, squishy cephalopods, most shells have evolved into interior features. Outsmarting or outswimming predators is their only means of defense. In fact, it is theorized that much of cephalopod evolution was spurred by predator avoidance. Blending in also helps when it comes to snagging an unsuspecting meal. Cephalopods can camouflage themselves in several ways. They use background resemblance, adopting colors, textures, and postures of the environment, as well as deceptive resemblance, molding themselves to resemble an object. They also use disruptive patterning, making themselves harder to distinguish from a complex environment. They also use counter shading, making themselves darker on top so that from above they're harder to see. The ability to change color and texture was probably the result of predator avoidance. But scientists have hypothesized that it has allowed cephalopods to develop a complex communication network based on appearance. However, this is more common in squids and cuttlefish than in octopi. On to the mimic octopus, found in the coastal waters of Indonesia. What a super fascinating creature! The mimic octopus can change both its color and its texture to blend in with its environment. It can also bend its body in all kinds of pretzely ways, mimicking other, more dangerous sea creatures such as poisonous sea snakes, spiky lionfish, or toxic flatfishes. They are also risk takers, often coloring themselves with bold patterns that could either scare away predators or attract them. In 2010, Christine L. Hufford and her team of researchers from the California Academy of Sciences conducted a study in an attempt to discover how the mimic octopus came to be such a shifty creature. They hypothesized that the mimic octopus's ability to use its limbs for camouflage came after it began using them to simply move. By using DNA sequencing, they discovered that the ability to change colors came first, followed by the simultaneous development of their long arms and bendy ways. Eventually, it all came together. The question still remains, however, whether the mimic octopus evolved specifically to copy the flatfish, or if it's all just a bizarre coincidence. Check out the video in the link below, and I hope you really enjoyed watching the first edition of Seaside Science. See you another day!